Hi everybody, how's it going today? I hope you're doing well. In this video, we're going to talk about multiple linear regression from scratch in Python. So again, like last time, we talked about simple linear regression. We implemented that from scratch. We saw how Scikit-Learn, that's the popular library, will do that for you if you import that, except we wanted to see how we can do it from scratch. And so we made simple linear regression, which is a simple technique to predict continuous values given one input variable. Now today we're going to look at something called multiple linear regression, which is pretty much the same idea as simple linear regression, except now we look at multiple variables. We use multiple pieces of information so that we can predict our one continuous value, and that could also be easily expanded to predict multiple continuous values as well if you wanted to. So today, multiple linear regression, it's pretty much just the same idea, but more complicated. So if you want to watch the previous video and you haven't done so, then go ahead, but I'm not going to recommend, or at least I'm not going to say that that's a requirement. I'm going to recommend you to watch that other video. If you have trouble with this one, then that one may help you out, okay? So again, I'm going to assume that you know nothing. Not that I'm assuming you know nothing. I'm saying that you don't have to know anything about Python, NumPy, Pandas, Scikit-Learn, these libraries, about the math and linear algebra or any of these concepts you may have heard. I'm not going to require that you know any of that stuff. This is intended as a beginner tutorial for machine learning and particularly in the idea of multiple linear regression. Now, do note that again, this is from a machine learning point of view. There is lots of other topics from a statistics point of view that you could talk about for multiple linear regression, but we're not going to really cover that. If you want to cover that stuff, then I would go to do a statistics undergraduate degree, or at least read a statistics book on regression itself, okay? So let's get started. I actually got started a little bit prematurely here. We have import numpy as NP, import pandas as PD, and here's our data set. We're going to use the same one we used for the other one, which is the California housing training data set. So remember that each row is some location in California. It has a longitude and a latitude, a housing median age, total rooms, total bedrooms, and so on. It has many of these variables here. I'm going to zoom out a little bit so I can scroll. Actually, I don't have to scroll now. So here, there's all the way up until the median house value. So last time we were predicting one of these variables. I can't remember. I believe it was either predicting total bedrooms or population. I believe we were predicting the total bedrooms. That's what we're going to predict today anyway. Okay, so we're first going to look at this idea called the correlation between variables. So if I do this thing and I have this stored in this variable called df, this data frame, pandas data frame, if I do df.core, and I always think of my friend Corey because of core, but here, so total bedrooms, we're going to be trying to predict this variable. So if I look at the core sub this variable, then what we get here is a series of values with corresponding labels here, where we have the correlation between, and I'll explain that in a moment, between total bedrooms and longitude, with total bedrooms and latitude, all the way up until total bedrooms sub median house value. It also gives this correlation with itself, which basically means it matches up perfectly. So these are all individual things where it's the pairing of total bedrooms and each of these variables. So if we look at it, for example, total bedrooms and total rooms, this means this value of 0.92, well, first of all, it's positive, okay? There's other negative values here, so this value could have been negative. It was positive. That means as one of these variables increases, total rooms, then total bedrooms would tend to increase as well. So we'd have like a positive slope. And the negative ones, so that would mean we have a negative slope. As housing median age tends to increase, we see that the total bedrooms seems to decrease. And that actually makes sense. If we increase the age, or how basically the oldness, I don't know if that's a real word, how long these houses have been around, we tend to have less bedrooms. And that makes sense because, you know, we probably are making rooms with more bedrooms now than we did used to be, okay? So there's lots of these other correlations. The ones that are of interest to us are anything with a strong correlation. And a strong correlation is ignoring the sign, whether it's increasing or decreasing. It's about how close this value is to, or the absolute value of this is close to 1. So 0.07 is not close to 1. That means there's not a very strong correlation. And 0.8 or 0.88, 0.92, 0.98, these are very strong correlations. So these are of interest to us. Negative 0.32 is kind of borderline. It's like, okay, there might be something here. But what we're going to look at today is I'm going to just copy in this code for you. We're going to look at, so first, don't worry about this too much right now. If we set bedrooms equal to this variable here, which is just the total bedrooms column, and then we drop total bedrooms, longitude, latitude, housing median age, median income, median house value. Why did we drop these columns? So that it turned into this, where we have just total rooms, population, households, and bedrooms left over. At the end, by the way, I placed that at the end on purpose, and that's how I did this, is basically I dropped it and then I added it back in at the end. And so why did we do this? Well, basically I only grabbed the ones that have a strong correlation here. I have total rooms, 0.92. I have longitude, or I got rid of longitude and latitude because they were these small, very close to zero values. And yeah, we only kept the ones with a strong correlation. Total rooms has 0.92, population has 0.88, household has 0.98, and I got rid of the other ones. Okay, so I just did that with basically keeping that in a variable, and then actually I never even used this copy thing, so I don't really know why I even kept that around, right? I don't think I ever used that. Okay, so that says the above exception, right? So this will happen if you start to run things by overwriting the variable name, and I'm just rerunning from the beginning to get that again. Okay, so we can do that, and remember the axis equals 1. This I threw in there because then it knows for sure to drop the columns in particular. So anyways, we got the data set down to this, and we want to perform a multiple linear regression. Well, we're not quite there yet. And again, first, like we did last time with simple linear regression, we do want to see how we would use Scikit-Learn's like proper library, which is how you'd actually go to do this if you were doing it in practice. And we'll get to that shortly, but for now I'm going to make some individual graphs. And again, I'm just going to copy some code in for you and explain that. If we import matplotlib.pyplot as PLT, that's our graphing library, and we do a scatter plot between the total rooms column and the bedrooms column, we can see here that yes, as we saw from the correlation, as total rooms tends to increase, the total bedrooms tends to increase as well. And now I'm just going to copy basically the same code. By the way, last time we didn't really use plt.show. You don't really need to in a Jupyter notebook, but it makes it look ever so slightly better. If I copy this in now, population of bedrooms, this is exactly the same thing, except I'm labeling and use X label for the X label, Y label for the Y label. Can't say that. Then that labels them as well. And so now I'll show population of bedrooms. So basically all I'm doing is plotting the individual graphs between this column and this column, this column and this column, this column and this column, because we're looking at how individually our inputs map to the outputs. So here I'll show it with population versus the total bedrooms. Actually, generally when you say versus, you usually say Y versus X. You would say total bedrooms versus population, but not a big deal. We can see here as population has to increase, total bedrooms tends to increase as well. And then finally, I'm just going to do one more, which is plotting households and bedrooms, setting the labels and showing it. We can see it's this weird kind of pattern here with the line at the bottom. As households tends to increase, we have total bedrooms increasing as well. Okay, so why did I do that? Not any reason in particular. It's kind of just to show some visualization for you. Now, to show how Scikit-Learn, how we'd actually make this multiple linear regression, where we combine the results of household, population, and total bedrooms to try and predict the associated total bedrooms value. This column here. So basically you would do, what we're assuming here is that the relationship is alpha plus some slope times this value, plus some slope times this value, plus some slope times this value is roughly equal to this. So it's a linear relationship. We'll talk about that. If you didn't understand that, don't worry, we will absolutely revisit that idea. Okay. But we're making a linear model, and to do this, I'll actually start writing some code. df underscore numpy is equal to df.toNumpy. Why am I doing this? Because we are converting to a numpy array, and df numpy arrays have a shape. So we have 17,000 rows and 4 columns, where that last column is our output or y variable. The first 3 are different input variables. If I get X train, and I'm writing train because this is the data set that's going to be used to train the model, X train and Y train is equal to df numpy. I can do a little trick here, all of the rows, and then up until the So remember, this is not inclusive. So basically it would grab, this means all the rows, and this means which columns do you want? I want 0, 1, and 2, the first 3 columns. That's what that means. And we also have df numpy sub colon until -1. Okay, xtrain.shape and ytrain.shape. We should see that we have a 17,000 by 3. I'm going to start calling this a matrix because a matrix is really just a term for a table, but table without column names in particular. It's just values. So that's what we have here, and you can see it. I can output xtrain. It's not going to output the whole thing because it's very large, but we can see it has 17,000 rows going down and then 3 columns wide. So it's the same thing as our data frame, at least the same, basically this chunk here, but it's in NumPy so that we can feed it into Scikit-Learn. Now, if you remember, what we had to do for Scikit-Learn last time was actually reshape it to be 17,000 by 1, because this time, last time it was just 17,000 comma. The input was that, the output is still that, and that makes sense, and we're happy with that. This time it's already in this form of, there's like another dimension here, 17,000 by 3, because it is naturally a matrix, and this is why Scikit-Learn prefers that idea. Again, if that didn't make sense, I wouldn't really worry about what I just said there. From scikit-learn.linear model, import linear regression. And remember, what I'm doing now is not what we would actually do to implement it from scratch. This is just showing the idea of what we would do in when we're actually going to do it in real life, like after this lesson. If you want to go do it and make a linear model, this is what you would do. And so we're doing this so that we see how to implement stuff from scratch, what we want to implement from scratch. So we'll make sklearn model is equal to a linear regression, bracket, dot fit with xtrain and ytrain. We can get the sklearn y predictions. So y is going to be the bedrooms, just generically, it's going to be y. Sklearn y predictions is equal to, I just wrote 2 equals, sklearn model.predict with xtrain. Okay, so we get its associated predictions after we fit it. So this is training the model. It's finding the best parameters, the best slopes for each of these different variables. We'll find actually an intercept term, an alpha. We'll find a best beta 1, a beta 2, a beta 3. And that's just what I'm choosing to call them. You could call them other names, but that's what we usually call them. And sometimes you use beta naught instead of alpha, but don't worry about that. We train the model, we give it the data. So the input matrix, what it maps to, the outputs. We get our predictions, where we actually call predict on the training matrix, which says for each of those, for each of these points. So for this point, these 3 inputs, what is the prediction? For these 3, what is the prediction? For these 3, what is the prediction? So we should have 17,000 results. And so we see if we have sklearn y predictions.shape, it's a NumPy matrix, or NumPy array this time, just a vector. A vector means just a long list of information. So 17,000 values. Okay, we have 17,000 predictions, and I can do this again safely. Here are actual predictions. And what we talked about last time, and I'll go over the idea again, but basically we need some way to measure error. And I'm not going to write our error measuring functions like we did last time. I'm just going to import them for you. Or we have, and actually I'll import both again. So from sklearn.metrics, and I'll actually let you see, there's going to be a long list here. We can see, well, actually, it's not showing you the right thing, so never mind. But we're going to import two metrics, which is mean absolute error. Mean means average, so on average, what's happening. Absolute error means either direction, so like absolute value, it means on average, how wrong is our model, how much are we off in the same units that the actual prediction or variable is in, so bedrooms. We'll import mean absolute error, and although we don't often or don't always use mean squared error, which is the same thing, but how off is it squared, this is generally what is being optimized under the hood, and we'll actually go to see that since we're implementing it from scratch. So we can ask what is the mean absolute error of, we'll say sklearn y predictions, and compare that to the actual y train, that is our outputs. So these are our observed actual y outputs. These are our predictions. Let's see what that is. And then I'm going to copy this and just replace it with mean squared so that we can see those results too. We're off by average by 40, about 40, 39.67 bedrooms. and squared, or off by average squared by 5,650. Again, less interpretable, kind of weird. This is what's the mean squared error is what's being optimized, because it's easier to optimize that function than the mean absolute error function. Now, like we did last time, we'll do the predictions df. Predictions df is equal to pd.dataframe. So I'm just making a data frame from scratch, and actually I see really no reason to type this out for you. I would like to copy this because it's just a lot of typing. So basically, predictions df is this data frame where we have the population is the population, the households is the households, the total rooms is the total rooms, the bedrooms is the bedrooms, that's our y variable. And so here, the last two columns, this last column here is Scikit-Learn bedroom predictions, and Scikit-Learn y predictions, I call it the same thing. So this should work. Basically what we have here is for each of these, this is our inputs, this is the observed output, and this is our prediction. You can see we're off by a lot there at the beginning, but we get a lot better near the end and also in the middle. Okay, and now what we did before is basically plot our line where we had, okay, our input on the x-axis and our output on the y-axis. It's not so easy anymore because our input is actually 3 variables. Each thing we're predicting is with 1, 2, 3 different values. Okay, so to actually plot this properly, you would need one axis going this way, another axis going that way, another axis going up, and then I guess that would be your 3, and then you could choose like a color or some sort of other way to represent the 4th dimension there. But it's a little bit confusing. You can see I'm talking a little bit weird. And more generically, if you had many more columns, then there would be really no way to plot this in a valid way. So we're not going to worry about plotting that data at all, really. So what we're doing is I'm going to basically just copy this in here to read this out to you. We're going to implement this from scratch now. We're assuming that total bedrooms sub I, so the ith total bedrooms value, whatever this is, bedrooms, this is equal to alpha plus some slope beta 1 times the associated population value plus beta 2 times the households value, households I, plus beta 3, some odd third slope, times total rooms plus an error. Okay, that's what we're assuming that total bedroom sub I is actually equal to. Remember, there's going to be some extra error there, and so I said plus error. But we don't actually want to model in the error. When we're trying to make a function that predicts it well, then we don't really want to have that included. So what we want instead, well, this is generally, I just wrote this generally as the output, basically just changing the population and households and total rooms and total bedrooms into like just x's and y's. So the associated inputs are just ordered for x1, x2, x3, and the output is going to be y. Now our model is y hat sub I is equal to alpha hat. So I'm writing hats here because we're basically trying to estimate these things. We're trying to find, okay, what's a nice estimate of beta 1? So we'll try to find beta 1 hat. What's an estimate of alpha? Alpha hat. And alpha hat is, or alpha itself, is basically our y-intercept. It's just some value that'll help us out. And the other ones are slopes associated with these input variables. Okay, so that's what we're assuming our model is. Note again, there's no error at the end here. We're not going to assume in our model actually help it predict with some random error. We're going to predict with this function, this line. So we're going to write this function together, which is getting predictions given some associated pre-existing model. So if that doesn't make sense, don't worry. We'll try to define get predictions with the model and x. And if you were with us last time, we had a model as a dictionary when we asked what alpha hat and beta hat was. But now we have just our model is going to be p parameters. It's going to be just this list and not a dictionary of the first value is alpha hat, second value is beta 1 hat, third value is beta 2 hat, and in total we have p parameters. Now, x is this matrix, it's a NumPy array, so like a table of floats with the shape n, so that's how many rows we have, how many data points we have, and by p minus 1 of inputs. Why is this weird and why is this annoying that I have to write it like this? Well, I do, because if we have a model, say that a model is p parameters, then our actual input matrix, how many columns we have, if you remember here, our model is alpha, so you can pretty much just pretend that alpha is here, alpha plus something beta 1 times this, plus beta 2 times this, plus beta 3 times this, P would be 4. We'd have 4 parameters, and the number of columns that we have for our input, this would look like our X matrix here, this thing. This has 3 columns, whereas our number of parameters is 4. So parameters is P generally, and number of P minus 1 is the number of input variables that we have. And we just want to return our associated outputs, okay? So for each row, we want that matched up. For each of these rows here, we want that matched up with a big vector, or not the whole thing, but we want this matrix to be associated with some vector, to return some vector of predictions, okay? So like we did before, it was this big long thing, this big matrix is X, and we want to be able to produce this vector Y. Sorry, I said that a little bit badly the first time. Hopefully that made sense the second time. So we want to get our predictions given our model and our output, where our model is this vector of information. Actually, I should draw a vertical line, as I'll show you shortly, and X is our matrix here. So I am going to go over to Paint and draw you a picture. Okay, let me try to draw you a pretty picture here. So if we have our input matrix X, where we have, how many rows do we have? We have n of them. So like this, I'm going to say this is n. And then how many columns do we have? We have P minus 1. I'm going to leave a vertical blank here at the beginning, and you'll see why shortly. So going across like this, we have P minus 1 items. So this should be, I'll write it as X1. So this is the first row. This first index indicates the row. The second one indicates the column. So this is X1, and it's going to be the first one. Okay, so the first variable, the first row. This is going to be X1, 2. So the first row, but the second column. And this goes all the way up until X1, P minus 1. Okay, so X1, this 1 is always the beginning because we're in the first row, and the second item is the column. X1, 1, X1, 2, X1, P minus 1. Now, if I fill this, basically, if I fill it like this, it's just a shorthand way to say like however many we have. This should go all the way down until this is Xn1. Okay, so it's the first column, so this stays the same. This is 1, but this is the row, so Xn1. This is X11, this is Xn1. This is going to be Xn2, and this is going to go all the way up until this is, what value is this? This should be, well, it's the nth row, and it's the P minus 1th column. So this is Xn, and then the second one is P minus 1. Okay, so it's kind of weird written like that, and I apologize for it being weird. This is a tiny math lesson, and I hope this makes sense. So this is our input matrix. It looks like this. We have our parameter, basically our model, which is a bunch of parameters. It's just a bunch of values we're trying to learn. We want to figure out these parameters. We're not worrying about learning them yet, though. This is just assuming that we have them given some particular parameters, which is, we'll say alpha. And actually how you would draw it, I'll draw it with hats. So this is why I'm saying hat. This is alpha hat, which is our basically intercept term. Beta 1 hat, which is our slope associated with the first column. So it's always associated with these variables, and we'll see why shortly. And this goes all the way down until, what is this value? If we have P parameters total, this is our P parameters, then this should be beta hat P minus 1. So there's P minus, sorry about that, P minus 1 things here, plus 1 is there should be P things. So it doesn't really match up right now because we have P things here and we have P minus 1 things this way. So we draw 1s here. Let's go, this whole first column is 1s, so that we'll see why for 2 reasons. The main one is because this whole thing now across, this whole thing is P dimensional. There's P things across, so that these two shapes match up. This is P and this is P. Okay, so what we actually want to do here is basically, if you can think about stretching this thing out so that it's horizontal. So if you stretch this out so that it's alpha hat and then beta 1 hat and then up until beta P minus 1 hat. If you stretch all this out sideways, basically think about pairing this thing up sideways with this row and then all of the rows here, so that it's always, and you do multiplication where they touch. So it's alpha hat times 1, which is just alpha hat, plus beta 1 hat times x11, plus, if there's a 2 here, beta 2 hat times x12, all the way up until beta p minus 1 times x1 p minus 1. If that was confusing, don't worry too much about it. But basically, we make this to be a pairwise multiplication with and sum it with this vector right here. So sorry about that. That probably didn't make sense. What we do is alpha hat times this plus beta 1 hat times this, all the way up until beta p minus 1 times this. And we do the same thing down here. Alpha hat times this plus beta 1 hat times this plus dot dot dot, all the way up until plus beta p minus 1 times this value right here. And so what that's doing is basically just converting this. If I write it like this, this is converting it to a vector, where if we do that multiplication and sum, like I said, this value here, this would be our prediction for the first row. Okay, so we have n of these things. This is going to be n-dimensional. We'll produce n rows here. And so that's the first prediction because it's our models multiplied and added with our inputs here. That's what we're assuming the relationship is. And this goes all the way up until yn hat. So these are our associated predictions. If this part didn't make sense, do not worry about it too much. I really don't think it matters too much. It's just a bit of a math lesson I wanted to throw in if it makes so that it could try and make sense. We are going to write this code. So basically, we can get our shape as we can do the tuple. We can get n, and it'll be p minus 1. P minus 1 is equal to x dot shape. Okay, because that's what we said it is. X is n by p minus 1. And then, of course, we can get p is equal to simply whatever p minus 1 is plus 1. So now that we have that as well. What we're going to do, we want to add in that column of 1s. So that column of 1s was important to us. So we're going to say new x is equal to the numpy.1s, which is simply a matrix of 1s, where we set the shape equal to n by p. Okay, so now we have n rows and p columns all are 1s. But to actually get back, basically what I'm doing is just trying to get this actual matrix. What we have is this piece here. We just have this 1s, or we're trying to add in these 1s. What I just did is basically shape this whole thing so that it's 1s, and then I'm going to override this particular section with the x variables. So I do that with new x is simply this to start. It doesn't have any x in it yet. What we'll do is new x sub all the rows, and then 1 comma, which says those last columns. So anything but this first one, all of these columns here, we're going to override that and set that equal to x. So that new x now is actually that proper picture here. And then we can do the math like we just said. What it's actually called is matrix vector multiplication. And actually, it's kind of a weird term in NumPy. But we're going to do call that with return NumPy dot dot of new x and the model. Okay, so you can picture this thing as new x here, and this is the model. And np dot dot will make this prediction vector so that it returns a numpy dot array of floats with the shape of n comma. That's what it does. Okay. I will run that and we can test it with, how do we do it? Test model. So just the test model is equal to numpy.array of, we're going to make it 4 items to match with our particular example. So I'll just get random values 1, 2, 1, and 4. So that's saying alpha hat, maybe it's 1, beta 1 hat, maybe it's 2, that's right. Alpha hat 1, beta 1 hat 2, beta 2 hat 1, and beta 3 hat 4. Hopefully I said that right. And we can get the predictions with our test model. So we pass it, how do we call it? We pass it the test model. And then we give it our input matrix, which is xtrain. Okay? And that makes a series of predictions with a shape of 17,000 comma. Okay, so n rows. Hopefully that makes sense. And so what this does is has predictions for a given model. This is just, we chose this model. It's just an arbitrary choice. It's not necessarily the best model, but it's an okay model. Or actually, no, it might not be okay at all. It's just, it's a model basically. What I'll do here is add to the predictions df, what we were observing before, the same thing, the get predictions with the test model and xtrain. It's that same thing here. And we can look at predictions df here's our predictions. Not very good. Okay, so 1283 was the actual, 14,000 was our prediction. 531, 8,400. It's really, really far off. And so maybe If these values are too big here, then maybe we could make a better model with maybe setting this to 1, setting this to maybe I don't know, 1.2. These could be floats as well. So let's try that. And we can see, clearly it got better, but it wasn't great. Maybe we'll set this to 1 over 2, maybe 1 over 3. I'm really just picking things to make it smaller. I don't know. Okay, and maybe it got a little bit better. It's still not great though. We can actually measure its error. So what I could be doing here is looking at the mean absolute error of, if we look at, what is it? I grab it as this, predictions df sub test predictions, this column here. If we look at that and compare that to y train, the actuals, then that gives us a mean, sorry, actually I want absolute, not mean squared. That's not so great. Mean absolute is off by 1861. Maybe I'll try to get a little bit better, and maybe this should be 1 over 4. So can I get better than 1861? No, that looked very, very similar. So I'm surprised at how similar that was. But anyways, okay, so here's our model makes these predictions with these inputs. We want to find better parameters, clearly. We're going to minimize the mean squared error function. And we do that with something that's very confusing. And I just want to paste this function in for you and read it, because I'll redirect you here. If you want to know the math, it will take a fair amount of effort. Kind of like you probably got confused with the paint picture. This would get very, very confusing on how to do this. The important part, and actually I'll save the implementation to not distract you from the important part just yet. We want to get best model, which is a function, don't worry about this import, that returns the model with the parameters that best minimize the mean squared error, that function. And so we have x is a numpy.array of floats with a shape of n p-1 of inputs. Those are our inputs as before. Y is the numpy array of floats with a shape n, comma, of observed outputs. Okay, so we give it, that's basically like fit before, and we give it the x and the y, and it returns a shape. It returns a little bit of a different object than Scikit-Learn does. This is just a vector of values, a numpy array of p parameters representing our model. It returns the best parameters that will minimize the MSE, assuming it's a linear calculation, linear formula. So how do we do that? It turns out we do it like this, and I'll just copy it in for you. Here you go. So this is the same thing as before. We get n and p. We make our matrix in the exact same way, so that new x is that paint picture as before. And then we do the numpy dot of the numpy dot of the inverse. That's the numpy dot lineage dot inverse of the new xt. So basically, this is a formula that's I've had memorized since it came up in my stats class. If you're interested in this, definitely take an undergraduate statistics course in linear regression. And basically, the formula is x transpose x inverse x transpose y. If you don't already, you probably don't know what I said unless you already know what this is, and then I wouldn't really be watching this video if that were true. So basically, transpose is what I said is a certain operation on a matrix, which is this. The inverse, there's an idea of the inverse of a matrix. It's also a matrix, and you can do matrix multiplication as well. This is matrix vector multiplication. You can also multiply matrices with themselves. It's kind of weird. I do not want to get into that topic. Linear algebra, statistics, all that stuff. What I just made for you is a function that basically emulates fit itself, the model fit function, like in Scikit-Learn. What we can do is test this thing with best model is the get best model, feeding it the x train and the y train, the observed inputs and outputs. We'll add predictions df, the best predictions, to be the predictions on with the best model on the training input. And then we do predictions df, and we can see that our model does exactly the same thing as Scikit-Learn's model. It gives the exact same outputs, so it's obviously okay. All right. And if we wanted to, we could look at the error on this model, which is the mean absolute error of the predictions df sub best predictions, so that column right there, and y train, and we could look at the mean squared error of it as well. And we could see that it's off by 40 and 5650 here. We see above, sorry for the headache, that above we got that, where is it? I did output that, right? It should be right about here. off by about 40 and 5650 right there. Okay, so we made a linear model, a multiple linear regression model, and sorry for glossing over the formula and making it looking very kind of skeptic. I don't like to do that, but I promise you that that was the right thing to do for this video, at least in my opinion. So, where to go from here? Basically, we did in linear regression, it was for predicting continuous values. The main point of this from a machine learning point of view is you have some inputs and you can make a linear model that predicts continuous values as well. So two things to note. Basically, we did only use input variables where these are continuous variables and not the idea of binary or categorical variables. I want to do a video on that next, so that'll probably be a shorter one, but I am going to do that, how to use those as inputs as well. And probably the video after that is going to be, right now we're only predicting continuous values, which is just, floating point values. But there's no reason why we can't do something called classification, which is trying to predict what class something is. So is this a cat or a dog? Is this fraud or not fraud? Is this, there's also multi-class classification, like is this a cat, a dog, a snake, a bear, whatever. And that gets, that actual idea of what's in a picture. Well, that's very complicated, but more so just, we're talking about the idea of trying to predict different classes. So like class 0, class 1, class 2, red, blue, green, any sort of idea like that, ignoring the actual model that's used to make that. The important part is that we're changing the output to not be a continuous value, but be either a binary variable, so 0 or 1, or some other class like 0, 1, 2, 3, and so on. So those are going to be two future videos. I didn't want to include how to use those two variable, or how to use categorical variables in this video. I wanted to make a video with that own title, and the one after that, we're probably going to implement logistic regression from scratch as well. And if you enjoyed the video, make sure that you drop a like. I'd really appreciate that. It helps a lot. And subscribe if you're not already, for sure. And I will definitely see you in the next one. If you liked this series of kind of just implementing stuff in Python so that you kind of understand it, not too much into the math, but a tiny little bit into the math, so that it doesn't make so that it's not complete mumbo jumbo, but not going so into the math that it's just, kind of diminishing returns at that point. So yeah, I'm lost for words. Like the video, subscribe, and I'll see you in the next one.